Hello all, we're at the end of chapter 4, which is Newton's third law. Many of you might know Newton's third law. The law basically is the law of what we call action and reaction forces. What it means is whenever something pushes on something, it gets pushed back. If I push on the wall is pushing me back. If I throw a football, the football is pushing me back. I'll give you an example. If I was standing on something that's on wheels, right, and I've got a heavy object, and I throw the object away from myself, I am going to go backwards. All right, so again, here's the situation here. So here is the person standing on an object, don't try this at home, that has on wheels. Nothing is moving, right? Let's say the cart has a mass of 10 kilograms. The child has a mass of 30 kilograms. And I take a 5 kilogram bag of salt and I throw the bag of salt that way. As I am pushing on the salt bag is going to be pushing me back. So if I look at the forces acting on the salt bag, there's the salt bag itself. The salt bag will ultimately have two forces acting on it, one being the planet, but the other one is going to be the force applied to the salt bag by me. If I look at the forces acting on me on the cart, or the child on the cart, right, the person that's on the cart, again, is free body. I need to draw the object onto itself, and there is a force being applied back. So if I apply a force of 20 newtons to the salt bag is going to push me back of 20 newtons. So there's Newton's third law, right? For every force, there's an equal and opposite reaction force, right? So we often look at examples of people on frictionless surfaces, which would be something like on rollerblades, right, or on skates, where the friction is very, very low. Right. So the textbook. Let's just go to our whiteboard here. Textbook gives us an example. Actually, our textbook. I've got a sample problem here from the other book, and it shows a person on skates, and I've got another person on skates, and one person, this person here, pushes that person on the shoulders. And what's going to happen is person on the left has a mass of 50 kilograms. That's person number one. Person on the right has a mass of 70 kilograms. That's person number two. And then the applied force that's being used here is 70 newtons east. I'm just going to use 70 newtons, and I'm going to use this direction. And the question is, state the action and reaction forces, draw the free body diagram for each skater, describe what will happen to each skater, and calculate the acceleration of each skater. So, we know that if person one pushes on person two, as I'm pushing on that person, I'm actually getting pushed back if I'm person number one. As much as person number two is experiencing a 70 Newton force, person one is experiencing a 70 Newton force. So if I was to draw a free body diagram for person number one here, right, this is person number one, they're going to have an applied force of 70 newtons. If I was to draw a free body diagram for person number two, having a mass of 70 kilograms, person number two is also going to experience a force of 70 newtons this way. Now notice that I'm not including the two other forces that are acting, which would be the gravitational force pulling down and the ice pushing back up for person 1, and gravity pulling down and the ice pushing back up for person 2, because as you can imagine, if we're just out on the rink at the arena and I push on person number 2, I'm number 1, neither of us are going to go up or down, right? Because the forces up and down will cancel each other out. So now if I look at person number 1 now, if I look at the rate of acceleration, so there's Newton's third law, right? Those are the action and reaction forces. There's our free body diagram to them. Skater 1 is going to speed up in the left direction as skater 2 accelerates in the right direction. And now we can calculate the rate of acceleration for both. So for person number 1, F net equals ma. F net is 70 newtons left. That's equal to the person's mass times their acceleration. The acceleration is going to be 1.4 meters per second squared left. Person number 2 is going to experience an F net equals ma also. The F net is going to be 70 newtons to the right. It's going to be equal to the person's mass, which is 70 kilograms, times the acceleration. And the acceleration for person number 2 is going to be 1.0 meters per second squared to the right. Okay, so you can see here that even though person 1 is doing the pushing, person 1 is ultimately going to have the greater effect to their body. Again, because the forces are equal and opposite, okay, equal and opposite, same magnitude, opposite direction, I can now look at the effect of the forces acting on both. So that's Newton's third law. Now I want to extend this a little bit, and I want to look at a situation where I've got a toy. The toy has got 3 parts to it, all on wheels. This one, and there's a little piece of string that connects this one to this one, and there's a piece of string that connects this one to this one, and then there's a piece of string here that the person can apply a force to and pull the whole train along. Okay, so when I'm looking at this, recognize there are 3 things here, 3 masses. I also have 3 pieces of rope that are actually doing the pulling and pushing. Right? I'm not actually touching, so I'm going to call them A, B, and C. So A is 1.0 kilograms, B is 2.0 kilograms, and C is 0.5 kilograms. And the person is going to apply a force of 5.0 newtons this way. Now, note that, like I said, there are 3 ropes involved here, and each rope is basically doing the pulling. So, remember, pulling and pushing are forces. So this rope here has a force. Whenever we've got a rope, we usually talk about tension. It's the force of tension, which is the force in the rope. Right? I'm going to call this force of tension in rope 1. Here, between A and B, I'm going to call this the force of tension in rope 2. And between B and C, I have a rope that has a tension or a force, which is the force of tension in string 2. Now, the question becomes, what is the tension in the strings, and how fast are A, B, and C going to accelerate? Now, this is a pretty standard question. It shows up on the test every semester. It shows up on the final exam most years. Right? And to do this question, we really need to be able to do our free body diagrams and analyze what's going on. Now, I'm going to make the assumption here that the frictional force is 0. Right? These are really good wheels on this toy. right? It was an expensive toy, and it's got great bearings, and there's very little friction in these wheels. In other words, if I pulled it, it would go for a long time before it stopped. Okay, so let's look at the overall, the big picture. So here's the person over here who's going to be doing the pulling, right, with 5 newtons. That's a 5, not a 6. Pulling with 5 newtons. And that person's pulling the entire toy. The entire toy has a mass of 3.5 kilograms. Because A is attached to B, which is attached to C. Remember last day I said whenever we've got a string, we're making 2 assumptions. One is the fact that the string has no mass, and number 2 is the fact that the string won't stretch. In other words, all it's doing is connecting one object to another and transferring the force from one object to another directly. So when I pull on the first string, T1, right, with my applied force, I'm here pulling on this toy, I'm pulling 3.5 kilograms. I'm pulling the whole toy. So if I was to draw a free body diagram here, I have the entire toy, which has a mass of 3.5 kilograms, and there's only one force that's working in this plane. Again, remember, FG and FN are going to cancel each other out, because when I pull the train forward, it's not going up or down. Right? So the only force here is FA, which is the 5 Newton force. So if I calculate the acceleration now of the entire toy, I need to look at the net force acting on the toy, the mass of the toy, and I can calculate its acceleration. I know the F net is 5 newtons. I know the mass of the toy is 3.5 newtons times the acceleration. And if I calculate my acceleration, it's 5 divided by 3.5, which is 1.4 meters per second squared. Forward. Now, I'm going to, for the rest of this question, assign a sign convention, which I probably should have done right from the get-go. It says forward is positive and backward is negative. So as it starts, the only force is the one that's in the forward direction. Right? But now I'm going to ask a couple of other questions. So if I said, how fast is part A, toy cart A accelerating? We'd say, oh, it's accelerating at 1.4 meters per second squared. How fast are B and C accelerating? They're also accelerating at 1.4 meters per second squared. Now, notice that rope FT2, right, is only having to pull that little toy at the end. It doesn't need to be very strong to be able to pull that toy. Compared to, sorry, FT3. Oh. This one should be 3. FT3 is pulling the C car, right, which is a little 0.5 kilograms, weighs almost nothing. So to pull that small amount of weight, the string doesn't need to be too strong. Notice that string 2 is having to pull the 2 kilogram plus the 0.5. It needs to be a stronger string. There's going to be a greater force in that string because it's actually pulling both the 2 kilogram and the 0.5 kilogram cart at the same time. So it needs to be stronger. And the string that needs to be strongest in total is FT1, or string 1, which has to pull the entire 3.5 kilograms. Right? So I'm sharing the force. It's not like the force is going to be used all the way through here. I'm going to share the force between the different cars in order to get them to accelerate. So if I was going to draw a free body diagram for cart C, here's cart C. Whoops. Here's cart C. Has a mass of 0.5 kilograms. It only has one force acting on it, which is FT3, right, which is string 3 pulling on it. That's the only force acting on C. Gravity and the normal cancel each other out, so I'm ignoring them. So if I said, what is the net force? Well, the net force, there is only one force. I have to add all the forces acting on cart C There's only one. So net force is FT3. F net we know is also MA. I know the mass is 0.5 kilograms. And I know the acceleration is 1.4 meters per second squared. So my FT3 now is going to be 0.7 meters per second, 0.7 newtons. Okay, that's the force in that string number 3. Okay, let's look at string number 2. String number 2 here, or cart B, let's slide up to cart B. Cart B, so here is cart B. We know it has a mass of 2.0 kilograms. And it's got two forces acting on it. Right? It's got string 3 pulling it forward, string 2 pulling it forward, and string 3 is pulling it back. Remember, FT3 was pulling cart C forward. Right? Why is it pulling cart C forward? Because B is pulling on the other end of the string. So what is that string doing to B? Newton's third law. If B is pulling on the string T3 is pulling B back. And we know that the force in T3 is 0.7 newtons, and in this case it's a negative 0.7. Where it was a positive 0.7 in the first cart, the force of tension is in the opposite direction for cart B. I also have a force being applied here, which is T1 string 1. Now, if I want to figure out what is the strength or the amount of force in FT2, well, I can look at the fact that the F net statement for B is going to be the two forces acting on cart B, right? Tension 2, which I don't know yet, and tension 3, which I know is negative 0.7. I know F net is MA. I know that cart B is 2 kilograms. I know that it's accelerating with the rest of the toy at 1.4 meters per second squared. So 2 times 1.4 is 2.8, and the negative 0.7 goes across to the other side. So my FT2 now is equal to 2.8 plus 0.7, and FT2 is 3.5 newtons. Now, I should be able to prove that this all works if I go to my third cart, which is my A cart. Now, I already know everything about this question. I know what the rate of acceleration is for this cart, for this cart, for this cart. I know what the magnitude of the force is in FT3, FT2, and FT1, because if I'm pulling with 5 newtons forward, it's pulling me back with 5 newtons. And what FT1 is doing is it's transferring my 5 newton force to cart number 1. But let's just say, for argument's sake, let's calculate FT1, assuming that it's not 5. We know it's got to be 5, but let's just go back and let's say, okay, let's look at what's going on here. So if I draw a free body diagram for cart A had a mass of 1.0 kilograms. A is being pulled by string 1 as being pulled back by string 2. Now, I know what string 2 is. It's right above there, 3.5 newtons. but it's now pulling cart A backwards. Where it was pulling cart B forwards, it's pulling cart A backwards, right? Newton's third law. So I end up with an FT2 of negative 3.5 newtons. If I do my F net statement for this question, I get F net for cart A is the two forces acting on it, FT1 and FT2. String 1 and string 2. And I know that F net is MA. I know that FT1 is unknown. I know it's 5, but we're going to prove that it's 5. And FT2 is negative 3.5 newtons. Now, if my mass for this cart is 1 kilogram, the acceleration is 1.4 newtons, FT1 minus 3.5 newtons. On the left, I've got 1.4. I've got the negative 3.5 on the right, which goes across to the other side, and I end up with FT1 equals 4.9 newtons. Now, it should be 5 newtons, but again, notice that because of some rounding, it's going to be a tiny bit off. All right, so what I've proved here is that Newton's third law is even working in this question here also. All right, so I'm going to get you to work on the two questions that I skipped earlier in section 4.3, which were questions 39 and 40 on page 146 at the end of the chapter. And then there is also questions 53 to 55 on page 148. 53 to 55. Oops. Okay, so there they are there. 39 to 40 on 146 and 53 to 55 on page 148. Now, I kind of like this rhetorical question here. Oops. Which says, if two objects are pulling on each other, right, let's say I pull on a shopping cart in the parking lot. Right, so here's me, and here's my shopping buggy. Okay, and I'm going to pull on the shopping buggy with 50 newtons, and I'm going to walk across the parking lot at constant speed. Or A equals 0. Or F net, MA, is also 0, right? Because F net is MA, A is 0 because V is constant. So I'm walking. Am I pulling on the cart? I'm sure pulling on the cart. I know it's there, right? If say it's heavy, I'm pulling on the cart. I know that it's there. So let's say I'm applying a force to the cart of, say, 25 newtons. Right? Let's get rid of some more of this stuff here. Okay, so there's the applied force on the cart. If I look at what are the forces acting on me, okay, the cart's pulling me back. Now, hang on a minute. If I was applying a force of 25 newtons to that cart, but it's not accelerating, that means F net on the cart has to be 0, which means if there's 25 newtons of my force pulling it forward, there has to be 25 newtons pulling the cart backwards. Okay, what is that 25 newtons? Well, we say, well, it's gravity. No, but gravity works. Oh my goodness. We know gravity's working this way, not that way. You say, yeah, but as the cart gets heavier, I have to pull harder on the cart. And in the next chapter, chapter 5, we will look at why the mass of the cart affects the amount of frictional force. But because the cart isn't going up or down, those two forces are canceling each other out. Because I'm not accelerating in the horizontal plane, I know if I'm pulling with 25 on the cart, friction must be working backwards against me. Right? And that is the horizontal components, and that's why it's going to not accelerate, but it is going to move at constant speed. You think, hang on, if there's no net force, how can it be moving? Because I had to apply more than 25 newtons to get it to the speed that it's going at, and then I'm going to back off my force so I can walk at constant speed. So when I first start pulling on the buggy, you know that it feels heavier, and then once you get moving, it's a bit easier to keep on moving it. Right? So there's the buggy. What about Mr. Cinna here? Now, if I look at, let's get rid of all this stuff. I need a bigger whiteboard. If I look at Mr. Cinna here, here's me. Whoops, here's me. And I'm pulling on the cart, so the cart is pulling me back with a force of 25 newtons. Oh, but I'm actually walking this way, right? And what's causing me to move? Well, that's the friction between my shoes and the parking lot. If you could imagine, sometimes you watch a cartoon and you see in the cartoon the person's legs spinning, but they're not moving anywhere. If you could imagine me being on black ice and trying to pull on that cart with 25 newtons, my legs would be going, right? But I wouldn't be moving anywhere. They would just be sliding on the ice. But as soon as I'm now on solid ground where I can get friction, the parking lot can push me forward. As I push back on the parking lot with my legs, the parking lot is going to push me forward. So there's actually a force forward of 25 newtons acting on me. Right? So that kind of looks at, well, why am I moving if I'm pulling on the cart with 25 and it's pulling me back with 25? There's a lot of 25s going on in this question. Right? But just recognize that because of this, F net is 0, acceleration is 0, and I can have constant speed, whatever that speed is, fast speed, slow speed, 0 speed, but it will be constant because